As far as I know, this doesn't exist. I have looked everywhere. I've got to the end of AliExpress, LCSC, Hackaday, YouTube, Reddit. I've even asked GPT. You can buy 14 segment displays, sure, in about 6 different colors. But the second you want all of them all at once, you're out of luck. As far as I can see, they basically don't exist. So this video is about what it took for me to build one anyway. This exploration of 14-segment RGB displays started as a side quest of a bigger project, a large LED message board that I'm building. And it started to bug me. Why am I picking a color up front? I wanted the retro aesthetic of a 14-segment display with modern RGB control. So I thought, how hard can it be? Well, for reference, this is an SK6805 addressable RGB LED. They're absurdly tiny, 1.5 by 1.5 millimeters. That's an index finger for scale. One thing that I wanted to do was keep the same size and form factor as the stock displays. The first real challenge was mechanical. I opened the datasheet and I immediately knew that there was going to be some issues. The mechanical drawing was pretty useless, too vague for precision placement. So I did what any reasonable person would do. I put the display on my flatbed scanner and calibrated the image. I rebuilt this in Fusion 360 and extracted the exact XY coordinates for every single LED's position. I hand-placed 1 out of 5 of the 14 character displays using the XY values from the mechanical drawing, and then I used KiCad's new repeat layout function that's slipped in since version 9, and that made the whole process a lot easier. One thing that's worth mentioning is I designed 4 different front PCB variants. These were going to be sent to fab at different thicknesses. One of them had vias between the segments, hoping that just one would work in this scattershot approach, and I would be left with some reference material on how LEDs diffuse through FR4. So I'm now going to jump into the ordering process. So you make your Gerbers and you upload them to JLC, and your board is visualized at the top. But we're not just getting a board made this time, we're also going to get PCBA assembly. This is because the LEDs are small and I don't want to have to hand place and check for accuracy on what is about 70 LEDs per PCBA. So this is the first time that I'm using PCBA assembly. So unlike normal Gerber uploading, this requires 2 additional files, a bill of materials CSV and a positions CSV. The positions tell the pick and place machine where to put the parts, and the BOM tells the machine what parts to use. So buying 352 LEDs ended up costing £18, and these are sourced from JLC PCB LCSC's factory. One thing that I thought was really neat is the JLC interactive tool actually lets you validate that the pins are in the correct orientation. This is really just a belt and braces approach to make sure that you haven't got the wrong orientation set up in your pick and place positioning CSV. So all in all, this turned out to be about £50. So for 5 pieces, it basically boiled down to £10 per single PCB that I got manufactured. Something that is useful to mention is from the time that I put the order in on the 25th of January, it took 10 days between order place and my boards being manufactured and on the plane to the UK. And then they were on my desk 2 days later because of the ability to ship internationally very quickly. And there it is. There is the first PCBA that I have professionally got manufactured for a home project. The fact that it arrived in the panel was really interesting to me. The panel was easy to break out because I used V-cut scoring. And then I had my own board that I was able to use. I very quickly got it up and running using an ESP32. And it was nice to see that all of the LEDs functioned. So we're going to talk about the diffusers. This is what the bare dies look like. They're very bright and they'll blow out pretty much any camera that's trying to record them. This is currently the 1.6 millimeter thick PCB. You'll notice that there's a high amount of diffusion because there is a large amount of actual PCB material between the LEDs and the viewable surface. This is going a little bit smaller now. This is the 1mm no wires variant of the front cover. You can see that the diffusion is reduced ever so slightly, but it's very hard to notice. The next one coming up is the 1mm with wires. The wires were put in place to try and act as a bit of a brake because they go through the PCB, so they can be used as a bit of a in the middle of the PCB shield for light diffusion. You can see that the effect is a bit better. Maybe that's a candidate for refinement in the future. And then this is probably the best one. This is 0.8mm thick. The general trend that I've noticed is if you're going to be doing this sort of thing with LEDs, it's probably the best idea to go for the thinnest PCB you can. That's the next thing that I'm going to look at taking forward. So this was a PLA print for the faceplate that was 2mm thick. The actual light pipes in the middle were also 2mm thick. The amount of light that is diffused into the white PLA is high, so it actually looks in person quite dim. This is me getting a bit better. What I've done is I've reduced the thickness of the front plate. As a consequence of that, more light is transmitted through from the LEDs to the front panel. But there was a few more iterations, and this is the one that I settled on that I'm really happiest with. This was 2mm border with a 0.3mm front diffuser. Translucent is not as good as white because you'll basically have that glare effect into cameras from the bare dye of the LEDs. So yeah, this is me showing, like, in Bamboo, how I took the individual elements for the 7 segments and basically shrunk them down. I didn't need to go back to the CAD tool because it was quite easy to actually change the values of it in the slicer. In a final closing note, I think that this could be made better by potentially making a mold and doing a 2-tone casting for the outer faceplate and the inner light guides. By doing it that way, I think you'd lose a lot less of the actual light from the LEDs because you would have a homogeneous material that is used to transmit the light from the die to the front plate. The other thing that you could do to improve the print quality is use a smaller nozzle on the Bamboo printer. This is me printing with a 0.4, maybe moving down to a 0.2 could get higher detail on the light guides. So thanks if you made it this far. This version isn't perfect, it's not cheap, it's not mass manufacturable, but it proves the idea works, and it gives me a reusable building block that I can drop into future projects. If someone's already done this at this scale, I'd genuinely like to see it, and if not, then at least for now, it's a reference point of what is possible with modern assembly and consumer-grade fabrication. This started as a side quest, and it ended up unlocking a whole new way for me to build things.